Hello friends, I welcome you to my YouTube channel MacPM. In this video we will calculate the bending stresses in the beam. So there is a given T section for a beam cross section, and here question is a cast iron beam of T section as shown in figure. The beam is simply supported. So we can see that beam is simply supported, means one end is hinge and other is roller support at a span of 8 meter. So it is 8 meter of a span. The beam carries an uniformly distributed load of 1.5 kN per meter. So uniformly distributed load is 1.5 kN per meter length at length entire span throughout the span. Okay, determine the maximum tensile and maximum compressive stresses. Okay, so what we have to see that first of all let's calculate the reactions for this beam. Suppose this is RA, this is A point, this is B. So this is RA and this is RB. From symmetry you can see that RA is equal to RB, or we can calculate also like sum of all the vertical forces is equal to 0 in this beam. So you can see that RA plus RB plus minus this is suppose upward is plus, then downward force is 1.5 into this total length 8. So RA plus RB is equal to 12 kN. This is equation number 1. Now if we take bending moment at about point B, then it should be 0 because it is roller support. So sum of all the bending moment about B is equal to 0. So RA into 8 minus 1.5 into 8 into x 8 by 2 is equal to 0. So RA into 8 is equal to 48. So RA is 48 by 8 is equal to 6 kN. Okay, so RA is 6 kN and RA plus RB is equal to 12 kN. So RB is equal to 12 minus 6 is equal to 6 kN. So RA is equal to RB is equal to 6 kN. Now shear force for this beam will be shear force at section X. Suppose section XX at X distance. Shear force will be 0, then bending moment will be maximum. We need maximum bending moment to calculate the maximum stresses, bending stresses. So we will calculate where the shear force is becoming 0 so that we can calculate maximum bending moment at that point. So shear force at X section will be RA minus W is 1.5 into X. So shear for X is equal to RA divided by 1.5. RA is 6 divided by 1.5 is equal to 4 meter. So at X is equal to 4 meter, bending moment will be maximum. So at X is equal to 4 meter, maximum bending moment will become RA into X. So RA is 6 into X is 4 minus W is 1.5 into X is 4 into X square X by 2 is equal to 4 by 2. So it will become 24 minus 12. So it is 12 kN meter. Now for maximum bending stresses, formula is M upon I is equal to sigma upon Y. So we already have maximum bending moment and we have to find I and Y. Y distance from the neutral axis, and we have to calculate this sigma. So we have to find I and Y. So first of all we have to calculate the neutral axis of this section. So suppose this is section 1, suppose this is section 1 and this is section 2. So y bar is equal to a1 y1 plus a2 y2 divided by a1 plus a2, and x bar will be in between this section because it is symmetrical about the y-axis. So we have to calculate only y bar. So y bar is equal to, see, a1 is 100 into 20, length into width 100 into 20 into y1 means distance of, suppose we are considering all distances from this point, so distance of the centroid of this section from here, so it is this 80 plus 20 divided by 2, so 80 plus 20 divided by 2 plus a2 is 20 into 80, 20 into 80, length into width into y is 80 divided by 2 divided by area is 100 into 20 plus 20 into 80. So if we calculate this, we will get 8180000 plus 64000 divided by 2000 plus 1600. So if we calculate, we will get 67.67 mm. So this is the distance of neutral axis from this point. So we have already denoted it 67.77 meter, or if we minus it from the 100, then it will become 32.23 from the top fiber, and from bottom fiber it is 67.77 mm. Now for calculating the sigma, which is stress, bending stresses, we have to calculate m, I and y. We have already calculated maximum bending moment, we have already calculated y. Now we have to calculate I means moment of inertia of this T section. So now moment of inertia I is equal to moment of inertia of this section 1 about neutral axis plus moment of inertia of section 2 about neutral axis. So suppose for section 1 it is I1 and for section 2 it is I2. So first of all we have to calculate I1. For rectangular section we already know it is BHQ by 12 about its own axis, but if we are calculating from about something different axis, then we have to add area into distance to the square. This distance is between this section, neutral axis of this section and neutral axis of entire section. So it is B is 100 into H is 20 to the cube divided by 12 plus area is 100 into 20, 100 into 20 into distance between, this is 10 from here and this is 32.23, so 32.23 minus 10 to the square, so it will become 66666.7 plus 988,345.8, which is equal to 1055012.5 mm to the power 4. Now we will calculate moment of inertia for this I2 for this section 2. So we will get BHQ by 12 divided plus AD square. So here B is 20 into H is 80 to the cube divided by 12 plus area is 20 into 80 into distance from the neutral axis is, its neutral axis will be at, centroid will be at 80 by 2 means 40, so 67.77 minus 40 square. Okay, so you will get 85333.3 plus 1 2 3 3 8 76.6 is equal to 208,709.9 mm to the power 4. So to get the moment of inertia of the whole section, we will add I is equal to I1 plus I2. So I1 we already had 1055012.5 plus 2087209.9, which is equal to 3142222.4 mm to the power 4. So this is I. This is moment of inertia of the entire section, and we have already calculated the neutral axis. So now we have calculated maximum bending moment. So we will apply just formula, which is equal to m upon I is equal to sigma upon y. Now we have drawn the beam already, and we have seen that we have calculated maximum bending moment, which is equal to 12 kilonewton meter. But you can observe that this is simply supported beam and load is applied downward, so beam will bend like this. So we can see that outermost fiber, downwardmost fiber is stretched, so here it will be tensile, and this is compressed, so here it will be compressive force, compressive stress. So you can see that on the top of the T section, here it will be compressive stress, and here it will be tensile stress. Okay, so maximum, first of all we have to calculate maximum tensile stress. Okay, so we have to see that maximum tensile stress will occur at this section, outermost section. So this distance is 67.77, so y will become 67.77. so sigma is equal to, sigma tensile is equal to my upon I. M we have already calculated 12 kilonewton meter. Okay, which is equal to 12 into kilonewton means 1000 newton into per, it is per meter. So if we calculate in mm, then it will become into 1000 mm, and y is 67.77 mm divided by I is, we have already calculated I is equal to 3142222.4. Here you can see that we had 12 kilonewton meter bending stress, bending moment. So 12 kilonewton, we can write 12,000 newton meter, and if we convert meter into mm, then we will get 12,000 into 1000 newton mm. Okay, I hope you understand how to convert this. So you will get 258.81 Newton per mm square. This is maximum tensile stress. Now maximum compressive stress is equal to m y compressive upon I. So here also we will get 12,000, 12 multiplied by 6 zeros, 226. This is m, and here in case of compressive stress, see, maximum compressive stress will occur at topmost fiber, so it is 32.23 mm upon I is 3142222.4 mm to the power 4. So if you calculate this, then you will get 123.08 Newton per mm square. This is maximum compressive stress. I hope you understand how to calculate the maximum compressive stress and maximum tensile stress for a T section. If you like this video, then please subscribe our channel. Thanks for watching this video.